We will talking about how the guardians of the BIOS are failing. We will discuss a few different ways. But if you don't know me, I working for Silence. I have a lot of fun with reverse engineering and firmware security, and actually I have 6 sweet CVEs in this talk for you. Okay, what my talk about? Actually, after a quick intro, we will be discuss some issues with BIOS updates, and I have few vulnerabilities in SMI flash Dixie driver and SEC SMI flash Dixie driver, which is actually responsible for the sign-in updates validation. And after that, we will switch in the Intel boot guard, which is actually, I think, most interesting part of the talk, because Intel boot guard is not documented yet. It was some stuff which is researchers dropped on public end of the last year, but I found few mistakes which is not appears in their work, and we will discuss how it's more details about how it works, and I actually make some bin diffing on authenticated compute models, ACMs, and we'll show you how we can recognize one-day vulnerabilities in the parsers inside the ACM models. And of course, I will show first bypass of the Intel boot guard on the public today. And another technology which is also undocumented and very interested is Intel BIOS guard, and we also will be touched today. So all the stuff which I discussing today in my talk, it's based on reverse engineering of American Megatrends BIOS for the different vendors, which is based on these technologies. Okay, briefly, actually, some historical overview on the rootkits. And all the rootkits actually want to be in the ring 0 because it's the best place to track the user activity without any complexity which you can have if you want to be in the SMM. And we already have loaders which load malicious payload to the ring 0 from ring 3. Then bootkits came up as a trend, and now actually system management mod, it's a very sweet place to be for implants and BIOS rootkits. And as you can see, a lot of researchers currently looking in this space, and we already have some leaks appears about real implants for the MacBooks, for example, on WikiLeaks with the Starka. And also mitigation of the modern operating system, like sign-in code policies and secure boot, make more harder the life for rootkits. And after the sign-in policies, more common became bootkits. And after that, when the secure boot appears, BIOS implants, it can be most interesting way to for evolution of the rootkits. And as we can see, all the rootkits now more closer and closer to the hardware. And of course, complexity is growing too. But let's discuss interesting things about the BIOS updates and where is actually problems here. So it's almost no more legacy BIOS we can find on the laptops and desktops, servers, and whatever. And now it's UEFI is everywhere, and actually UEFI ecosystem is huge. But what? Now we have legacy inside the UEFI world, and that's actually true because UEFI is huge, and also each IBV have a lot of different hardware, and it's kind of painful to update. And BIOS developers, not all of them, but a lot of small companies more focused on the boot time, not security. And the lifetime for the BIOS updates for some of the vendors, it's very short. This picture actually shows how many different firmwares can be exist in the BIOS update image. And actually, it's not only BIOS. As we can see, it's ACM models for boot guard, BIOS guard, TXT. It's microcode updates. It's management engine. It's graphics networks if they are embedded into the motherboard or PCH. Also, embedded controller, even like power management is get updates from the BIOS. And if we actually have any problems with BIOS authentication or any way to install the malicious update, actually it can be a first start to deliver the malicious update for all of this firmware. Because if any mistake from the developers in these firmwares, so you can get in. And this stuff will be discussed today and touched in the presentation. Okay, all vulnerabilities which we will discuss today is based on American Megatrends BIOS, and we have a few vendors which our representation is covered. It's Gigabyte, Asus, Lenovo, and MSI, and we found vulnerabilities for all of them. On this slide, you can see all the guardians of the BIOS on one slide. Actually, we don't have too much. If we don't speaking about the runtime mitigations inside SMM and the BIOS protections in runtime, we have pretty much not a lot of them. And mostly, first layer of protections, it's simple security bits, BIOS logs, BIOS write enabled bit, and SMM BIOS write protection bit. Also, we have policies for spy flash regions like PRXs. And we have two technologies which is actually very complex and interesting. It's Intel Boot Guard and BIOS Guard, which is much more hard to bypass it. And of course, signing updates and updates authentication is very important, but not all of the vendors care too much about that. So we have two CVEs for the really simple security bit checking, but this simplicity, it's not mean the impact can be small. And I will show you on the next slide. Also, these vendors don't actually use the PRX registers for spy flash protection, and it's, in my opinion, not the right way, because exactly these policies can be not rely on this SMM protection and can protect BIOS even if spy flash regions, even if somebody already installed implant, but spy flash can survive. Sign an image looks like not a big deal, but not all of the vendors are doing that. And of course, Boot Guard. We get two CVEs, which is managed to help us for bypass this technology. One is for ME management engine, and one for the Boot Guard. Okay, we make some research how many vendors use the different ways these simple protection bits, and as you can see, Asus Tech, MSI, and Gigabyte don't use too much, and also they have problems with updates authentication. Not all the hardware from them is the same, but overall, a lot of platforms from them come in without simple authentication and BIOS security bits is enabling. And no one is using PRX spy flash protection. Also, I've been surprised, actually, Apple don't use BIOS lock and also SMM BIOS write protection bits, but PRX they're using only for write protection. Okay, some of the vendors like MSI just don't care. They actually don't use any of simple security checks. Okay, what's wrong? They really think it's low security impact? I don't think so, because I'm already disclosed some POC about UEFI ransomware on Black Hat Asia this year, And first layer, it's been BIOS lock not enabled on these platforms. And then attacker can get in with a malicious BIOS update if it's not authenticated. And actually, I use SMI handler to update this platform, which is being exploited from legit signed driver from AMI, because they calling for the update a specific handler, but you can change in the memory and call any of SMI handlers from this driver for the update, even if you want to exploit. Okay, but what's new for this talk and how update guardians is fail? The thing is, we have like a ring tree application which is installed and registered the kernel mode driver, and this kernel mode driver communicate with the BIOS, specifically with SMM driver, SMI flash, or security SMI flash. The difference between two of them, it's security SMI flash verifying the signature, digital signature for the update, and SMI flash driver is not. Okay, but what if these SMI handlers can have vulnerabilities? Then you can escalate privileges to SMM with these drivers and actually modify in runtime their code to use it and update the BIOS. As example, security SMI flash, if they do have vulnerabilities, you can bypass verification for digital sign and deliver the malicious update. Okay, briefly, how this Dixie drivers works. They have interface with a different functionality, but most interesting is read, write, and erase. And by red color, I highlighted the vulnerable SMI handlers, which can be exploited, but already patched by these vendors. And yeah, actually, today is the disclosure date for these vulnerabilities, and as all the vendors already patched the vulnerabilities except one. MSI actually don't reply on our emails and don't provide any updates for their BIOS and vulnerable platforms. So looks like we are right. They just don't care. And it's the issues for security SMI flash driver, and actually all of three SMI handlers being vulnerable on ASUS platform, and actually all the hardware which we tested for this talk based on Skylake and Kaby Lake, and Kaby Lake actually exactly this ASUS platform being released on January this year. It's pretty recent hardware. They already patched this vulnerability, but it looks like ridiculous. Okay. If we have vulnerabilities inside the driver, which is validates the digital sign for the updates, what we can do? So that's why BIOS Guard been created for armoring this kind of processes. Okay, we found all of these vulnerabilities in April this year, and then started disclosing these vulnerabilities. We also communicate with Intel PCert, and they are actually very helpful for us to push in the vendors to update the BIOS. And ASUS released the patch in June. And actually, it was some fun with them, because they released the patch, but 1 month before, we sent them the 3 different vulnerabilities for the same driver. And then they just patch it silently and say it's no vulnerabilities for their products anymore. We say, okay, fine, but we sent to you like a month ago, and now you patch it after a month, and now, of course, it's not vulnerabilities, but we communicate earlier before. I make some pressure in Twitter, and looks like it was helpful. After that, they send us update and say, okay, guys, it's you discover these vulnerabilities and help us to patch it. Yeah, responsible disclosure, it's kind of fun. And now let's talk about the Intel Boot Guard. My opinion is most interesting part of this talk. And actually, why this technology has been created. Here's different shades of secure boot. And first secure boot actually came up in 2012. And if you talk about the attack surface for this technology, it's been like firmware. Any vulnerability for SMM, which allows the attacker to elevate the privileges to system management mode, can bypass the classical secure boot implemented on UEFI. And after that, actually, Intel created a boot guard technology, which is armoring secure boot from the attacker, and two different modes. Measured boot, which is more rely on TPM, and also have attack surface as a firmware. And verified boot, it's more interesting scheme and more actually hard to break it, because here is no more only firmware. Now it's actually root of trust, and attack surface rely on the firmware and hardware. And configuration for Intel boot guard locking by field programming fuse. Okay, and we will show today first bypass for verified boot. So actually, briefly why boot guard been created. Actually, I'm already discussed on the last slide. But anyway, secure boot starts from the Dixie. And Dixie, actually, it's almost the last phase before the actually BIOS passing control to the operating system bootloaders. And it's when actually attacker get in SMM, so SMM rootkit or any malicious payload can attack this phase, and any implants or rootkits can be an issue. And no verification actually for early boot for platform initialization and security boot phases. And measured boot actually start from the pay phase, which is also not an earliest one, and it can be impacted by SMM issues too. So the root of trust should be locked into the hardware as verified boot do. And the first step of verification should rely on the microcode authentication. And as we can see on next picture, not this one, it's locked in hardware and rely on the microcode authentication. But actually, in 2013, Intel presents the boot guard technology, and this screen actually shows all the information which came up on the public. It's not too much. And I actually decided a long time ago to make a reverse engineering on this technology. And boot flow with active boot guard looks like that. So we have a CPU reset. And after that, actually, CPU microcode verified boot guard ACM, authenticated code model, and authenticated code model actually passing control to the reset vector. And all these steps actually locked by hardware. And after that, IBB, its initial boot block, check the sec and pay phases platform initialization, and passing control to the Dixie phase, which is the Dixie drivers for the BIOS, and where is the original secure boot being created. And after that, only OS loader. So these three phases are locked by BIOS. What kind of mods, operating mods for the boot guard we do? So we have a measured boot, which is rely on TPM. We have verified boot, which is rely on the field programming fuse. And we have actually two of them, which is measured, plus verified boot, which is actually more strong mode. Okay, in 2015, Intel dropped on the Intel IDF forum this picture, which is actually very interesting, and we can see like different policies as appears, but it's not really clear what is going on. And this part actually is locked by field programming fuse. This part is initial boot block, and policy engine on the beginning is ACM. Okay, and it's actually what this previous slide says specifically, and we can see on PCH we have field programming fuse. Actually, it's the register which is store hash of the OEM public key. And into the firmware we have two manifests. First manifest is K manifest, and a second manifest is initial boot block manifest. And actually, these arrows show how the root of trust locking into the hardware. And we will discuss all of them a little bit further. And this locked by hardware, and this locked by firmware. And interesting thing, actually, Dell last week dropped some details about their implementation of Intel BootGuard. And it's almost like same thing which we covered. But it's good they dropped some details, and now we know how it works, and our reverse engineering work is correct. But let's check how actually guards configuration on the tested hardware looks like. And actually, our main target platform is Gigabyte. As we can see, management engine is not locked there. And also, we don't have a BIOS guard enabled there. And boot guard not locked into the hardware with a field programming fuse. Wow, interesting. By green color highlighted the scheme how it should be. So ME access should be disabled, embedded controller access should be disabled, and actually boot guard configuration should be locked by hardware. Even if it will be not enabled, it should be locked or disabled. But trust no one, because actually even if vendor claim they have boot guard enabled, it can be wrong configuration, which is allow attacker to bypass and lock some rootkit inside your hardware forever, because it will be not allow the updates from the vendor anymore. Okay, and I want to make a reference for the work of Alex Yermolov on the last year Zero Nights, because they show some interesting thing about the boot guard. They found empty configuration, which is don't have OEM public key hash and not locked. So if you and this platform specifically, which they're showing, don't have BIOS update verification, then attacker can just deliver the malicious update with the rootkit and flash inside the malicious configuration and lock the fuse. That's it. So, okay. Actually, I like this phrase from Greg. Attacker never actually attacks the specification. We always attack the implementation, and we found the vulnerability inside the implementation of Gigabyte hardware. Okay, but before we go in deeper, let's discuss how K manifest and initial boot block manifest looks like. BootGuard actually have the K manifest, which is have IBBM hash and RSA root public key, and RSA signature from key manifest security version number. And actually, security version number, it's a number which is locking this configuration if the fuse is programmed. And you can't actually change anymore this manifest or install another one which will be signed by the same key, because version number also signed it. Okay, we have also initial boot block, which is cover the integrity for initial boot block. And actually, it's exists in the boot policy manifest, and we can see here like IBB hash, and this green color highlighted the offsets for initial boot block. So we have the beginning and the end from the block, which is have a hash inside this manifest. And all the structures being recovered by reverse engineering, all the templates for 101 hex editor will be provided after the talk on the GitHub. Also, UEFI tool actually can parse this K-manifest, not parse, but find, because feed firmware interface table, it's public and documented on EDK, and these offsets we can find inside the firmware update and reconstruct the structures. This slide demonstrates how actually initial boot block looks like. And by red color, it's offset, which we just discussed from the beginning, and the end of the block, which is protected by initial boot block. And initial boot block actually protect from the beginning of the pay phase till the end all the drivers. And that's mean like we have ACM, which is protect initial boot block, and initial boot block protect all the pay phase. And now we actually, attacker not allow anymore to modify pay drivers to install some platform initialization phase rootkit. Okay, but most interesting part also it's like authenticated code model. What is actually this code is doing? It's have entry point, it have a ACM header, it does RSA public key, and even we can reconstruct the exponent and RSA signature. I tried to find some Blachenbecher attacks on this exponent, but actually it's created properly. So, okay, if this model have entry point and it's x86 code and ACM actually created by Intel, it should be interesting place to look into. So, actually ACM code executes in ACRAM, and it's usually it's the cache. ACM executes in the specific place cache as RAM, and it's non-invicted mode. ACM also have some specifics on specific CPU model and chipset. And ACM verification, actually ACM verify the key manifest plus initial boot block on very early phase before actually BIOS get start booted. I developed some interesting model for loading ACMs into the IDA, and I will release this loader also after the talk. Actually, it's a graph from entry point, how it looks like, and this code actually very connected each other, and it's few parsers inside because ACM parse feed header, find by feed offsets the different manifests, key manifest and boot policy manifest. And so it's a call graph from the entry point. We have actually get key manifest, get IBB manifest, parse them, verify, and it's actually pretty complex things. Then like we need the boot guard and make a platform in it and pass the control to IBB. To reset vector. And I start thinking, okay, I have IDA, I have a BinDiff, thanks Google for make it open for everyone, not open sourced, but free for everyone. And okay, I have a Haswell and Skylake ACMs, why not do a BinDiffing? But I've been not lucky, and here's like no lot of changes. I start thinking, okay, and probably some dependencies between microcode updates and ACM models. And I start thinking, okay, let's find some old BIOS update where is microcode being also not updated and probably ACM updated with microcode in the same way. When I start make a BinDiff on Broadwell, versus Skylake ACM, I've been more lucky and get more information. As you can see, like here is a lot of differences between these of two. And okay, I start actually different specific functions, and I found a lot of changes inside the parsers, and it's like a lot of addition sanity checks, a lot of some of these patches actually patch the integer overflows in the parsers, and it's perfect way to actually found one-day vulnerabilities and authenticated code models. Also, I tried to actually get old version of ACM and install on more recent with more recent BIOS update or downgrade the BIOS update, but it's different story. Some of the experience it's been success, some not, but it's a lot of fun. Okay. Next, actually, it's bootguard components inside the BIOS, and we have 3 of them. One is working on PAY, one working inside the system management pod, and one in the Dixie. Let's start from first one, how it's worked, and actually PAY make a validation flow and prepare also the transition of root of trust to the Dixie phase. And please pay attention on the piece of code which is highlighted by red color, because I have some intention to drop today like not a 0 day, but half of 0 day and few next slides. Actually, PAY verify the firmware hash key, which is also cover almost all the BIOS update. I recover this structure from the PAY code of the driver. And most interesting part, how many drivers is covered. And as example, if the BIOS developer make a mistake on the window for the coverage of, like on the beginning of set, on the end of set, and miss one of drivers, the attacker can use this driver for install the rootkit. Next thing, actually, it's how SMM validation flow works. And we have actually find and verify ACM, and we have like verification for key manifest, and we have a boot policy verification. If something going wrong, it will be raised security violation. But why we actually need this functionality inside SMM? Because when you reboot the platform, it's not always rebooting from the CPU reset. Sometimes it's like soft reset and start rebooting from them, not the first stages of the boot the platforms, which is actually not execute the ACM, but this driver actually checks the ACM being executed correctly. And here's the bootguard DXE validation flow. And one interesting thing, on this slide, you can see highlighted by the red color, code which is actually raise some flag about correct validation, and then actually prepare transition to the Dixie phase. And what if the platform going to S3 to sleep and not to reboot? It will be actually almost all the PAY phase will be taken from the cache and not executed from the beginning. Okay. Probably it's one more interesting bug. So, and in this bootguard DXE, which is actually based on American Megatrends implementation, they just checked the flag, it's true or false. If it is false, they actually call the callback, which is will be in the boot process raise some violation screen about the bootguard policies. But if not, it will be just success. And also, if attacker can elevate the privileges to SMM, and actually change this flag in this Dixie driver. So it can be interesting flow to actually bypass the bootguard from this phase on the resume. It's information about our target platform. And it's Gigabyte 6th generation, Core i7 with the Skylake and vPro is enabled. And this actually hardware have bootguard enabled, but don't have exist the bootguard or BIOS guard. But actually, this CPU should should actually have enabled the BIOS guard too, but it's not. And two vulnerabilities which is allow us to bypass the boot guard. One, it's read-write access to the EMI regions, and it's allow us to change the fuse because it's not locked. And another one, it's actually fuse is not locked. This screen shows the information from memory management info tool. And we can see like host read and host write, it's enabled for EMI regions. And okay, another interesting thing actually in the payload further recovery is also enabled. And we see actually the boot guard is enabled. OM key is there. And we have like most strongest mode is enabled, like measured boot plus verified boot. But the fuse not locking this configuration inside the hardware. So everything is enabled. Gigabyte actually have interesting proposal for this hardware. It's like for the schools, for the universities, for the governmental, for the hospitals. Imagine like if in hospital, very, very expensive hardware can be locked with the rootkit, with a malicious update, and actually nobody can recover this hardware, but as example, this hardware needed for the surgery or whatever next few hours. It can be very serious issues. Okay, how we can bypass the boot guard? I actually discussed it already, like we need a memory management read and write to be able to check and modify the programming fuse if it's not being programmed already. And also, we already recover all the manifests and all the key structures for all the main components. We just recalculate initial boot block, we modify root key, we actually don't need even like recalculate all the things. We can just clean up and log the rootkit with empty configuration, but it's not fun. We can actually recalculate all the things, make a proper configuration for the malicious POC. And so if the lock is not enabled, we don't have any hardware root of trust anymore. We just rely on the firmware, and all these structures actually exist in the BIOS updates. So this means attacker have access to them. And I want to say thanks for Intel PCert because they actually provide me some statement, and they say they provide to manufacturers specification and how actually IBVs should log boot guard updates and make proper security for the platforms. So that's cool, but still not all of them follow this specification. Here is a Gigabyte statement, and they literally say they changed some manufacturing process because of our issues, but we'll see how it's called. The problem is they don't include this functionality into the update. They ask user to log the EMB. And how many users actually know what is management engine is? I don't think so too much. But if not, they will be just not actually fix this issue on their platforms. BIOS guard, if it will be enabled on this platform, it can help, because BIOS guard, the technology which is being created for armoring space flash access, and also have some ACM model, which is actually attack surface for the firmware now it's actually from the firmware moving to the hardware because ACM module for the BIOS guard authenticated by microcode. And BIOS update authentication, even like if the BIOS update is not signed, but BIOS guard is enabled, BIOS guard will be authenticate the BIOS update by their policies inside the image. So it's all the information which is exist about the BIOS guard from the public, from the Intel. It's actually not too much, and I also decided to get deeper with the reverse engineering tools. And what we have actually with ACM module, we have like a lot of different PAY, Dixie, and SMM drivers. We have like 7 of them, and bootguard has just 3 components inside the BIOS. I mean, like in PAY, SMM, 1 on PAY, 1 in SMM, and 1 in the Dixie phase. And BIOS guard has actually 7, and it's like raised complexity a lot. Here is information with the GUIDs, but let's check what actually these drivers are doing. Some of them make a capsule update validation. Some of them help to recover update image parser, have image update recover parser, and BIOS actually CPU policy override have functionality to find the public key, find and load BIOS guard ACM. SMM actually have some also SMI handlers for updating and recover to SMM. When, as example, the PA phase not started, but this validation happens every boot for like verify that like we have right ACM model for the BIOS guard, and when we want to install the update, this verification will be happens. Also, the interesting part, we have recovery helper on the Dixie and also some ACPI helpers, which is mean like some ACPI tables, BIOS guard using some ACPI tables and information from the ACPI tables. And interesting part actually, BIOS guard actually also using some UEFI variables, and they start naming with the BIOS guard something if you found, so it's actually can be indicator the BIOS guard is enabled on this platform. So BIOS guard commands, we have recovered some commands from the PA and SMM, and it has like enable update or disable the update process, read, write, and erase the spy flash. So that's mean like we have some functionality which is still exists into the BIOS to use some kind of relation with the spy flash memory. It's pretty interesting information. So all this stuff include all the templates for 101 hex editor, and also the loader for ACM will be released on GitHub by this HTTP link. And I want to make some summary about current state of the biosecurity. In this Black Hat, actually, researchers talk a lot about the Black Hat security. Intel present the presentation BIOS is new black, because actually they have information about how will increase numbers of vulnerabilities for the BIOS. And what I want to say, we can see literally, like, we have some simple checks for the BIOS security bits, but we also have very complex technologies, and these technologies like have some components which is not rely on the BIOS security. Some of them exist inside the BIOS, and it's code written on C. So we have some space to research more here, and this technology is not documented, but I think for researchers it's very interesting to get in. Thank you very much for your attention, and I really appreciate you come for my last talk. And any questions? I always like how many questions I get on my talks about the BIOS, but I hope you guys enjoy it.
So Alex, the chipset and all of this?
The question is, chipsec will cover all of this? No, not all of this, but some of the actually checks, simple checks for the BIOS log bits, and also chipsec has SMI fuzzers, which can allow to attacker or on validation flow discover some simple vulnerabilities. But now actually it's a time where it's almost gone, and we need actually change some tools and experiment more on them. Okay, I'm done with the talk, and probably I will be. Okay.
Hello. So.
Hello.
I'm wondering. I feel a bit bad asking this with the Intel people, the UEFI people sitting in front. But have you looked at heads, the core boot payload presented at CCC last year? And do you know if this would sort of sidestep some of these firmware problems with Secure Boot and Intel Boot Guard?
So first, core boot don't have support for Intel Boot Guard, and they does some different way to develop the verified flow for kind of verified boot scheme. And I actually don't look too much on the core boot because in enterprise world, it's more common like UEFI BIOS based on Phoenix or American Megatrends, and I'm more focused on this code. So actually, I don't have answer for you.
Thank you.
Hey, do you have any ideas for cleanup for implants or anything like that? Maybe along the lines of core securities research a couple of years ago, backdoors and such, or even legit software like CompuTrace or whatnot.
You know, actually, it's a very good question. Actually, what I see with current state of implants, we don't have any security products inside the BIOS, which inside the BIOS or operating system level for scanning the BIOS, validate the flow, and found the vulnerabilities or implants. Problem is, if we base the product on already known information, that means the attacker, if they learn something new, already ahead of us, and it's a big problem. More about that, because like if we check in from the operating system and attacker already inside our BIOS, that's literally mean like they can fake all the information which we get on the operating system. So my opinion, the future for the scanners should be like BIOS developers, like hardware vendors should like implement something inside the BIOS which will be make validation or like maybe something which is not inside the BIOS, ACM, whatever, which will be validate the flow for the malicious implants. And I think it's very important, even for now, like when we want to travel outside of US, we need leave our laptops in the luggage, and we don't know who will have access to our hardware. If you have any more questions, I will go to the media room right? And I will be happy to answer all of them. And thank you very much for coming.